Let me share my screen first. You see my screen?
Yes.
Okay. So let's have a couple of minutes for any questions. We have the quiz graded, so you have it on Blackboard. You have the answer for the quiz. So if you have any questions in these, check your answer. Read the comments, please, at the end of the quiz of your solution. And if there is any problem, just get back to me within this week. I made an assignment for the submission of the bonus task at the report, so it's there. Make sure you submit it before the deadline if you want these 3 points. The final report is due next week. So please make sure your team is working to submit on time. We will finish the configuration layout today, and next time we're going to have a better weight estimate and estimation of the performance parameters of the aircraft. So let me see if you have questions, whether in the project or in the topic so far.
Victor, do you have a presentation or only a report?
Yes, the final, as we specified at the very beginning, it's a report and presentation. It's going to be a short presentation, probably on Wednesday and Sunday. Wednesday, week 15, and Sunday, because we have a class scheduled on Sunday as per KFBM calendar so far, which is a normal Wednesday class. So yes, there's going to be a short presentation. I think I mentioned the timing for that, the duration, probably no more than 15 minutes per team. And we will need, no, maybe 10, because this class has like 5 teams, so probably 10 minutes per team. You can always show a design in whatever time. You can show it in 1 hour and you can show it in 5 minutes.
دكتور
Yes.
بتعطينا فيدباك على البروجرس ريبورت؟
Yes, by Wednesday, all teams will get a written feedback on the progress report. Yes, showing the numbers that seem to be okay, numbers that seem to be incorrect, and where to look for mistakes. Yes. That feedback would be more on the final results. The best feedback that you get is when you guys start asking questions. I had several teams contacting me. We arranged several team meetings. They have questions. I look into their Excel sheet. That's a much better feedback. So if you are in doubt of a certain value, you want me to check a number, just send me this. Don't wait to the report. Okay. Any questions?
Victor,
Yes, no.
the requirements for the weight of the plane is like 1,350 pounds.
Yes.
Our team got it more by 15 pounds. Is it okay, or should we make adjustments?
It's not adjustment that you will do now. We all are going to do adjustments on Wednesday. We will better refine the weight. If the weight then is still above the 1360, then yes, we will make adjustment. Why I'm not eager for you guys to go and do adjustment, because in the initial phases of design, we did a lot of assumptions. Any one of these assumptions can bring the weight down if we tweak it slightly. Okay, so it's not going to help if we go and do this. What we will do next week, next Wednesday, is that the final configuration, the final dimensions of the actual aircraft that we have is going to be used to find the new weight. This is the one that's more accurate. This is the one that I will worry about if it's above the 13, even with a single pound. Why is that? Because 1360 is the limit by the regulation agencies for light sport aircraft. If it's 1370 pounds, it's a different category. It will not be licensed under light sport aircraft. Okay, and that would require different certification issues. So if you want it in this category, it has to be 1360. So don't check it now. The difference is not that much. Probably will go down a little bit by Wednesday when we do the refinement of the weight. Okay, we have a written question here. Okay. Any questions? Okay. Okay. So today you are finishing the last of the steps of the configuration of the layout. Over the past few sessions, we sized the wing. That means when I say sized, we picked the airfoil and we found the dimensions in inches or in feet of the wing. Not just ratios, but the dimensions, the actual dimensions. We found the weight of the aircraft. We found the length of the fuselage, the sizing of the engine, and the remaining parts. Let me stop for a second. I have two of your colleagues who cannot join the session. Let me try to get him in. I will wait for a second. Please hold on for a second. I will try to bring him in. Okay, I think they're here. So today we are finishing with the last two components, basically the propeller of the aircraft. We are going to determine how large is the propeller, as well as the sizing of the landing gear. What is the shape of the landing gear? Where are we going to place it, and how big the tires and the wheels are for this aircraft? So we will worry about the propeller sizing, wing placement, landing gear placement and sizing, and we're going to show the final layout of the aircraft. We are still here in the configuration layout. We will finish it today, inshallah. Wednesday, we are going to take, inshallah, step number 5, the better weight estimate, and on Monday, the performance analysis. We satisfied all the requirements in the process so far. We maybe have exceeded the requirements. We are not sure, and we are going to check next time. So moving on with the propeller, if I ask you what type of propeller you are going to have, are you going to have a 2-blade propeller that has 2 blades only, or 3 or 4? So first we have to make that choice. And the rule of thumb is the fewer the number of blades, the better. If you can satisfy all the requirements and all the constraints on the propeller design with only 2 blades, that would be better. Would be better because it will mean higher efficiency of the propeller. The propeller efficiency decreases with the number of blades. Think of it from the point of view of air approaching the aircraft. If he sees only 2 blades, This is less obstruction than if he sees 3 or 4 blades. Okay, so the fewer blades should be our first choice. So we should start always with 2 blades. If you can satisfy all the requirements with 2 blades, so be it. If not, try 3. If not, go with 4. Now, what are the constraints that we need to satisfy? There is no condition in the requirements that says the propeller. No, there are some conditions. One of them is the requirement of size. The propeller cannot be extremely large such that the blade would hit the ground. Right? So it should, you have some clearance under the propeller. It shouldn't hit the ground. The second requirement is that the fastest point on the propeller blade should have a speed less than the speed of sound. Now, the fastest point on the propeller is not at the center of the propeller, it's the one at the tip, because the speed is omega r. The more r you have, the more speed you are going to have. So it is the tip speed. So the tip speed has to be less than the sonic speed. The final constraint that we have to worry about is the matching between the propeller and the engine. The bigger the engine, we expect the propeller to be bigger. You cannot deliver 500 horsepower to the air through a small propeller. So if the engine has more horsepower, the propeller should be large. I always give this example, is very similar to your car. If you have a huge car, V8 in your, a huge engine in your car, V8 engine, for example, okay, 300 horsepower something. You cannot put on this tires that are R13, just like small cars. It simply would not deliver that power. Okay, so propeller and engines have to match. These are the 3 constraints. If you can satisfy them with 2 blades, so be it. If not, go for 3. So let's start one by one. The first condition that we will satisfy in this example of 5-passenger aircraft we are designing is the horsepower matching. So this is what you see on the screen now is an empirical relation. By empirical means it's not like rigorously derived. There is no mathematical derivation, but it's the typical industry norm between the diameter and the horsepower. So for example, if in your project, if the horsepower is about 100 horsepower, so that tells me the diameter of the propeller would be around 70 inches, because the unit of this equation of G is in inches. So I would put 100 horsepower to the power 0.25 times 22, probably gonna be 100 inches, which would be 2.5 meters. No, 100 inches? No, I think it would be less than this, maybe 70 inches. Okay. So that would be like 1.7 meters. Not bad for a 2-blade propeller. Not bad in a sense that I believe with the dimension that we have, well, we'll have enough room under the propeller. But I have to keep that dimension in mind when I put the length of the landing gear. Okay. For 3-blade propeller, we have a different equation, and there are similar equations for 4-blade and more propellers. So in this design, we will start by 2. So by 2, we will put the horsepower of this example that we have. 360 horsepower gives me a blade, a propeller with diameter 8 feet. Now 8 feet, that's about 270 centimeters, 260 centimeters, considerably large propeller. Okay, so we picked the horsepower. Let's check this diameter. Will it satisfy the other 2 requirements? What are the other 2 requirements? The tip speed should not be beyond the sonic speed, and I should have some clearance under the propeller. Let's check the tip speed. Now, what is the speed of the tip of the propeller? If I ask you, point on the propeller is rotating. What's the speed of any point on the propeller? Give me the equation that you had in your math or dynamics courses.
Omega R.
Omega R, right? Now, if I tell you what's omega r of a point on the tire of your car, you will not be able to tell me because you don't know omega, but you know the RPM of the engine. And you don't know r, you know the diameter of the tire. So basically the tip speed, yes, you are correct, it's omega r, but here it's written in different ways. R is d over 2, so there is 2 in here, and omega is 2 pi times the frequency, 2 pi times the revolution per second, 2 pi times the RPM over 60. So RPM over 60, that's the frequency, rev per second, times 2 pi, so that would be the omega, times d over 2, that would be the radius, and the 2 will cancel. 2 from d over 2 and 2 from the 2 pi. So at the end of the day, this is the equation that we typically use in order to find the tip speed of the propeller. It's pi RPM over 60 times the diameter. Since I already had the diameter, since we typically know the RPM values from engine manufacturers, RPMs for aircraft engines, similar to that of car engines, about 2000 something. So 2600 for this engine. The diameter is 8. I can determine the tip speed to be 1089 feet per second. Is this above or below the speed of sound? Let's say at sea level. Is this above or below the speed of sound at sea level?
I think it's below.
Yes, it's slightly below because the speed of sound at sea level is 1117 feet per second. Okay, so slightly below. So on paper, we satisfy the requirement. This diameter is good. However, it's not quite. We compare the speed due to the rotation of the propeller only. But there is another component of speed. Remember, this aircraft is moving forward. So if you are the point on the tip of the propeller, yes, you are rotating to the side of the propeller, but you are also moving forward with the aircraft. So the net speed in this case is the 1089 squared plus the forward speed squared under root square. Why didn't we add them? Because they are not in the same direction. The forward speed is pointing forward, and the omega r is pointing to the right or to the left, according to the direction of rotation of the propeller. So if you have two forces that are perpendicular to each other, the net speed, sorry, two speeds, not forces. The net speed is the root square of their squares. You see that? So it's just like getting the resultant of two speeds, the forward speed and the speed due to the rotation. Now, if you do this, the speed becomes 1149, which is above the 1117 feet per second. So that 8 feet per second is not good. Sorry, that 8 feet diameter of the propeller is too much. We have to make it shorter so that the rotational speed becomes smaller. You cannot change this speed because that's the forward speed of the aircraft. That's the requirement. You cannot mess with this. I have to change that. Okay, so I have to reduce the diameter of the propeller. But how can I reduce the diameter of the propeller if I have to deliver the same power? Easy, use 3 blades. So 2 blades is not enough. We will use 3 blades because the number in the 3 blades is smaller. If I use the 3 blades, the diameter becomes 6 feet. If I calculate the tip speed of the 6 feet, the 1089 drops to 889. When combined with the forward speed of the aircraft, the net now is 962 below the speed of sound. So we can have now a 3-blade propeller that delivers the horsepower 360 and rotates at 2600, and the point on the tip of the propeller will be below the sonic speed. Any questions up to this point for the sizing of the propeller?
In terms of the sizing, do we care about the pilot view?
Well, that's an interesting question. Would the diameter affect the pilot view? or the number of blades?
No, the diameter.
Really? Because no matter what, it will cross the field of view of the pilot. Because the engine is just like in front of the pilot. So if the diameter is 2 feet or 6 feet, it will still cross the field of view of the pilot, unfortunately. Okay.
Doctor?
Okay, I will just finish off here. If the field of view of the pilot is an issue, let's say, Extreme, you have like 4 blades, 5 blades, 6 blades, very few aircraft would have that, and you are worried about the field of view of the pilot, then let's make it a pusher type. Move the propeller and the whole engine backward. Remember, we had that option at the beginning. We could have put the engine in the back. One good thing was then that to improve the visibility from the pilot side. But the diameter really does not affect that of the pilot, especially if the engine is mounted on the wings. Of course, in this case, it's not an issue. Okay, yes, the other question.
How can we know if the blades will hit the ground?
A very good question. Up to this point, I really don't know, but I should have like a sense or an estimate of how long the landing gear is going to be. Let's see if the 6 is reasonable or not, or 6.5. See, I'm going to jump to the drawing. This is the aircraft that we were planning to have, right? So if I say the diameter is 6.5, that means the distance from here to the tip of the propeller is 3.2 feet. That's about 110 centimeters. So do you expect to have more than 120 centimeters from this point downward or not? Well, let's see. We know that this height is about 2.5 feet because we had the height of the fuselage, right? So 2.5. So all I need to do to make sure that the distance from here downward is more than 1.5 feet, which is about 45 centimeters. Do you think that we are going to have more than 45 centimeters below the belly of the aircraft? Probably yes. So probably we are okay with the clearance. But you are correct, we are not sure unless we design the landing gear. That's why the landing gear comes here right away. Okay, and to tell you the truth, it's an embarrassing truth, but it happened in 427 before, because the landing gear comes at the very end of the design project towards the submission of the final report, the propeller also. So you had teams, one working on the propeller, the other one working on the landing gear, and there is bad communication within the team. They don't communicate with each other. Everyone does his work, put his dimensions, someone will draw and they bring it to the final presentation, and comes the embarrassing moment when they show it on PowerPoint and everyone sitting would realize that this propeller is too big for this landing gear. It will definitely gonna hit the ground. And they find this, oops, when they are presenting the final report, which is kind of embarrassing. Okay. Okay, now before we leave the propeller for the landing gear, one last remark that I have to make here is we say the limit is the sonic speed. Well, it's not always the speed of sound. Sometimes we require lower limits. Sometimes if we are worried about the structure of the blade and we want to reduce the vibration, for example, when the blade is made of wood, not composites or metal, we may go below the 1100. We can say maybe let's put the maximum to be 900, for example. If the noise is an issue, because the higher the speed of air on, the speed of the propeller, the more noise it will generate. So if noise is an issue, you might even bring that limit down even more. So for aircraft taking off from small airports within the city, very near to houses, sometimes we require the tip speed to be maybe below 800 feet per second. Okay, so the speed of sound is just like the absolute upper limit, but we can go lower if we want to improve the noise level and if we want to reduce the vibrations. But of course, we will have to pay the price. The price will be more blades in this case. Okay. Okay. The last part is the landing gear and the wing placement. And you will probably be asking, why do we have the landing gear and the wing together? We already designed the wing. Yes, we designed the wing, but we did not place the wing. We said the wing is going to be a low wing. Yes, but we didn't say where are we going to put it. Is it going to be here or here or here? At what distance from the nose is our wing? We did not specify that. Okay. The same for the landing gear. In order to do this, we have to first understand what are our different options. Just like when propellers, we knew we had options 2 blade, 3 blade, 4 blade. Just like in tails, we knew we had T-tail, conventional tail. In engines, we can have the engine in front or the back. Also in the landing gear, we have options. One option is what we call the tricycle landing gear, where we have the aircraft touching the ground when the aircraft is on the ground on 3 points. 2 main wheels on the sides in the back and 1 nose in front. In this case, the CG would be in between the main wheels and the nose wheel. Probably it will be closer to the main wheels to make the reactions on them much more than the reaction of the weak nose wheel. If you look at this aircraft from the top, these are the touch points with the ground that you will see. The 2 main wheels and the 1 nose wheel. We call this the tricycle configuration, and it's very good in the sense it is stable. That's why all kids' bicycles are tricycles, because they are stable. Now, the other configuration, which was typically used earlier, and sometimes it still be used, is called the tail dragger. In a tail dragger, we have the main wheels pushed forward together with the wings, and then we have a small wheel in the back. In this case, the aircraft will be inclined at a setting angle with the upcoming free stream. Now, this configuration has a problem, is that it tends to be unstable on the ground, especially when the pilot hits the brakes. Imagine you are a pilot in this aircraft and he hits the brakes. What's going to happen?
The nose will go down.
Yeah, the nose tends to push down, and you probably seen this in World War II movies where an aircraft landing on an aircraft carrier, the hook arrests the cable, stops suddenly, the nose hits the ground. Okay. So it is unstable because the forward motion on the CG makes it rotate about the nose, the main wheels. So why people use this configuration? Because it has some advantages. One advantage is that it's giving the aircraft and the wing an initial setting angle. That means it's giving it an angle of attack to the air. So the aircraft can take off real quickly, because if you have an initial angle of attack, that means alpha is high, CL is high, the takeoff distance is short. So it was good back then. Okay. Now, the third configuration is what we call the bicycle configuration. In this bicycle configuration, we have only 2 wheels, 1 in the nose, just like the Harrier, and 1 main in the fuselage, just 1 in the middle, in the back. Now, this configuration is good if you have a high wing, because if you have a high wing, it's not practical for you to have main landing gear attached to the wing, because the landing gear you see is going to be very long. And if the main landing gear in here, you will not have room to store it when you retract it, because it's very long. So for an aircraft like this, it has the main wheel in the back, the nose wheel in the front, so that's why it's called bicycle. And the 2 supports on the sides are not considered a part of a landing gear. You see, when you look at the top, you don't see them small points. These are just like the supports you have on your young brother's bicycle when you start teaching him how to ride a bike. They don't carry much load. The main load is on the main wheel and the nose wheel. So that's why it's called bicycle landing gear. And it's good whenever you have to use a high wing. Here in the Harrier, we must have a high wing because the nozzles are movable so that they can push the air downward and the aircraft can vertically take off and land. So because of the high wing, they resorted to the bicycle landing gear configuration. So out of this, you have to pick one for your aircraft before we go. Now, for an aerobatic aircraft, you can have the tricycle and you can have the bicycle. And many aerobatic, the tail dragger. Many aerobatic aircraft have tail dragger configuration because it's simple. It does not require the retraction of the third wheel. Only these can be retracted or sometimes can be fixed. They are not retracted. Okay. But for our example here, for the 5-passenger, it was chosen to go with the 3 landing gears, basically the tricycle landing gear, because it's more stable. You have a passenger aircraft, so you want it to be stable. So any question on the choice of the landing gear before we proceed to sizing of the landing gear?
Doctor,
Yes.
for the aerobatic aircraft, which one is better?
What do you think?
I think the tail dragger.
Well, have you looked at the aircraft that you have collected the data of similar aircraft? Did you look at the pictures?
Yes.
The majority of these aircraft are what type?
I don't remember.
Well, they are tail dragger, just like you have guessed. So you made a good guess.
Okay.
Okay, so that doesn't mean that all 5 teams have to go now and make tail dragger. No, well, it could be a tricycle. But remember, in your design, the landing gear is not going to be retractable. So if you have a tricycle, the 3 landing gear are going to be protruding from the aircraft. And why we are not retracting them? Because the retraction required hydraulic system. Hydraulic system adds weights, and this is a very light aircraft. Okay. Okay. Now comes the question. We have chosen the type of the landing gear. Where are we going to place the landing gear? Now, to answer this question, we have to know where is the wing, because we will probably retract the landing gear in the wing. And because of the nature of the relationship between the wing, the CG, and stability of the aircraft. Since we haven't taken a stability course in here, simple introduction in AE220, let me remind you of the following. There are several important points along the length of the aircraft. One of them, of course, is the CG, and we have found the location of the CG of this aircraft from last time. Okay. The other important point is where is the wing, and when I say where is the wing, where is the aerodynamic center of the wing? And the aerodynamic center is the quarter chord point of the mean aerodynamic chord, not the root, not the tip, but the MAC. So where is the MAC? Where is the quarter chord of the MAC? We call this the aerodynamic center. Now the stability of the aircraft is related to the relationship between these 2 points as follows. And we are going to have the equation here without proof. We will be using it and you will derive it in stability courses. Probably you have seen it in AE220, but you will see it again in 426 and 313. The relationship is like this. The location of the aerodynamic center, XAC, of the wing body without the tail, is equal to the location of what we call the neutral point. I will get to that in a second. That's the third important point, minus the volume fraction of the horizontal tail times, what is A? Remind me, we have seen A before in this course. What is this A? A is what? Chapter 2. What is A?
It's the slope of
CL alpha slope, yes. Yeah. So CL alpha slope of the tail over CL alpha of the wing. Now this relationship relates the location of the aerodynamic center to a point called the neutral point. The neutral point is a fictitious point beyond the CG, so it can be here or here or here or here. The neutral point, xn, is the point after which the CG cannot move. The CG can move a little bit to the back or a little bit to the front, or maybe when you burn more fuel, it will move back. The CG will change as the aircraft goes, right? You can burn fuel, you can drop a bomb, shoot a round from the machine gun, you can throw someone out of the window, whatever. The CG will start moving, but If it crosses the location of the neutral point, the aircraft will be unstable, cannot be stabilized. So think of the neutral point as the aftmost position of the CG. Okay, so the relationship here, in this relationship, what do we know? We know CL alpha of the tail, because we have airfoil of the tail, we know the shape of the tail, we have enough knowledge how to calculate CL alpha, chapter 2. We know CL alpha of the wing, we know the tail volume coefficient, we determined that last time. So there is a relationship between the neutral point and the aerodynamic center. Okay, so what? How can we use this? Well, there is another relationship between the location of the CG and the neutral point. It's true the CG cannot cross the neutral point, but it cannot be very far from the neutral point. The distance between the CG and the neutral point determines how easy to control the aircraft. So we call this the static margin. The static margin is the distance between the neutral point and the CG divided by the mean aerodynamic chord. For reasonable handling of the aircraft, that ratio should be 0.1. What does that mean? What's the physical meaning of this? Let's see that. In your aircraft, any one of you remember what's the mean aerodynamic chord? What's the value of the Mach? Roughly. The chord of the wing, the average chord of the wing. Is it 4 feet? 3 feet, 4 feet? Anyone?
I think it was 3 feet.
Okay, let's say 3 feet. Okay, I think it's slightly higher, but let's say 3 feet. If it's 3 feet, 0.1 of 3 feet is 0.3 feet. That's about 9 centimeters. So what we have here, for reasonable handling of the aircraft, the distance between the neutral point and the CG, that means the distance from here to the neutral point, should be around 9 centimeters. Now that's a small distance, but it makes all the difference. If that distance is 20 centimeters, the aircraft will be too stable. That means it will be not responsive. You push the elevator, it will pitch up or down slowly. Maybe that's not what you want. If it's the 9 centimeters becomes 4 centimeters, then it will be highly responsive. So with a sudden elevator movement, the aircraft will pitch up or down real fast. So you can see that this number here determines the responsiveness of the aircraft. Fighter aircraft, aerobatic aircraft will tend to have lower of this value, lower value. Transport aircraft will be higher. So maybe transport aircraft, a large 777, maybe this value would be 0.13. An aerobatic aircraft like the project that you have, maybe this ratio would be 0.07. Let me put you in perspective. An F4 Phantom has a 0.04. Okay, so you know now the range where it is. We are talking in a very small distance. Now, if the distance is negative, that means if the CG moves behind the neutral point, the aircraft becomes unstable. Okay, so that static margin is very important. Now, with only these two relations, we can locate now the wing. How are we going to do this? Remember, we know the location of the CG. Okay, I know now where I should put the neutral point so that the distance is 9 centimeters. So I know where is the neutral point from here. When I know the neutral point, I will substitute in the first equation and I will determine where is the aerodynamic center. And as such, I know where I'm going to put my wing. So that's the whole point. That's why they are all related together. So from stability, the neutral point in this aircraft, which had a CG at 7.87, the neutral point has to be at 8.3. So that's about 0.6 feet behind the CG. And with this value would give me an aerodynamic center of 7.69, slightly ahead of the CG of the aircraft. So now I have placed the wing. Any question in the wing placement? Okay. With the wing placement comes the landing gear. Now we have to put now that we know where is the wing, where is the CG, we have to place the landing gear. Typically, the main landing gear will be slightly behind the CG. So the CG here is at 8.3, sorry, 7.8. So this one was chosen to be about 50 centimeters behind the CG, about 8.9 feet. The nose wheel will be very far forward so that it will have less reaction on the ground, because the weight on the CG will be divided between these two. The main wheel will carry more because it's near the CG. This one will carry less because it's far. So we tend to put the nose wheel as far forward as we can. This one can be even here forward, and in this case it will retract backward. But in this problem it was decided, let's make it a little behind and retract it forward. So in this design, the landing gear will retract forward. So that's why we have a distance of about 2 feet, because we expect the height here to be about 2 feet so that it can rotate and stored below the engine or in front of the engine. So it is in that room that we have in here. Okay. Now, don't tell me why this is 8 point, don't ask me 8.9, why it's not 8.8. Well, you can have it 8.8. Okay. So it's not like an equation that will tell you this number. But once you settle on this number, it will affect the calculations that we are going to do from now on. For example, it will tell me what is the force that's going to be applied on the wheel. Why? Because the CG, where the force acts downward, this force will be carried by these two supports, just like the problems that you had in statics. There is a support in here, a support in here. Can you how do you determine the reaction that is carried by this support? And I'm talking structures now. Mechanics. How do you determine the reaction on this wheel? If you know this weight is 100. I have support here and support here. How do you determine the reaction on this wheel? No moment, yes. We take the moment about this point. So the 100 multiplied by the distance is equal to the reaction multiplied by the distance, and this will give me the reaction. So this is what we will do. If this is the weight, this is the reaction on the main, F main, and this is the reaction on the nose, F nose. If I take the moment about point A, I will get the F main. If I take the reaction about point B, I will take the F nose. Since I know the weight, I know all the distances, I can determine both forces, the force on the main, force on the nose. Okay. Now, why are the forces important? Remember, these forces will change if I move this wheel a little bit behind. If this is not 8.9 feet, if it's 9 feet, for example, that will mean the distance will change and there will be less load on the main wheel and more load on the nose wheel. Okay. So these forces are important because they determine how big the landing gear is. So with these loads, I should go and check with manufacturers. I want a tire that will carry that load. How big the tire should be. Okay. But before we do this, please don't fall in a very simple thing that students usually forget, is that this reaction that we are having here is not a reaction on one wheel, it's the reaction on two, because I have two main wheels, one right and one left. So the number that we are getting here must be divided by 2. So the F main, which is 4,300, divided by 2 is 2,150. So you need each tire of the main wheel to carry 2,150. And the tire on the nose wheel, 857. If you have 2 nose wheels, then you need to divide this by 2 as well. But we have only 1 nose wheel. So we ask manufacturers, I want to carry this load in the nose wheel and this load on the main wheel. How big the tire should be? If you go to Banchar and you want to buy a new tire, he tells you what type of car you have. So they have like table, this car will go with this tire, this car will go with this tire, R13, R14 or whatever. Okay. So it's exactly the same here. We have a relationship between the load on the tire and the diameter of the wheel or the width of the wheel. Okay. And this relationship is in terms of 2 parameters, A and P, constants these are like typically from the industry. For example, your aircraft has a maximum weight of 1360. So maybe your weight you calculated in the progress report was about 1200, 1250. Maybe that will mean the nose wheel is going to carry 200 or 200 something. And each of the main wheel will carry about 500 or 550. So the load W on each wheel, main wheel, is about 500. If you put this 500 and you have A and B, I can determine the wheel diameter. I've just did it in calculator on section 2 an hour back, and it turned out to be about 13 inches, close 13 point something inches. And for the width, we also used the 550 weight per tire and give us a width of about 5 inches. So that means the tire of this aircraft, the aerobatic aircraft that you are having, will probably be close to the size of a tire of a small car. Size of a Yaris, for example, car. That tire is the same for your aerobatic aircraft. Of course, it's a different type of tire, but I'm talking about the dimensions. Now, for this problem that we're having, for this example that we're having, for the 5-passenger, the numbers are different. The tire is 2,150. You see, each tire in here is carrying almost double the weight of your whole aircraft in the project. So it has to be bigger. So if you look at this tire and we use the A and B, it will tell me the main wheel is 22 inches and the width is about 7.5 inches. Okay, and for the nose wheel, the same turns out to be 15 and 5.8. So that's this sizing of the landing gear. We have answered the question, what type of landing gear? Where are we going to place the landing gear? And what's the size of the landing gear? I'll stop here to see if you have any questions in the sizing of the landing gear. Okay, so now we have everything to draw the aircraft. Now I can get the full drawing. Last time we determined what's the length of the aircraft, so I can know the length. What's the width? I can find the width. We have designed the tail last time. What was the area, the span, the chord root, the tip chord. We did the same for the wing. Today we located the wing itself. So we know exactly where this quarter chord point is going to be. We have designed the landing gear, how big they are. We have placed the seats. We know we will retract the tires in the wing and the nose wheel will retract forward. We have designed the propeller. And the question that came earlier today, how do we know that it's not going to hit the ground? Well, we draw the propeller here with the dimensions that we had, and we ensured we have at least 6-inch clearance. Should be at least 6 inches, about 15 centimeters below the propeller until the ground, maybe more, but that's the minimum. And that's it. That's the resulting layout. 3 weeks back, we started with only the requirements, and now we have a full drawing of the aircraft. And when we were discussing the type of design, conceptual design, students had the impression that conceptual design means you take a piece of paper, a pencil, and draw a sketch of the aircraft, just like artistic drawings of the aircraft. And they always tell them no, conceptual design is a full design of the aircraft's main dimensions, main components, to ensure the requirements will be satisfied. What remains now is that we are going to take this design and we are going to do analysis on it. What do you mean by analysis? Analysis, that means problem solving. The stuff that you always did in quizzes. I can take this design with my choices right now and study what is the takeoff distance. I will go and calculate it. Maybe it is the same that we have to satisfy, or maybe it's more, maybe it's less. So I have to check that. What is the total weight of this aircraft? So I will now know where are the seats, where is the landing gear, how big the landing. I will start put all these weights and I will find the total weight. It will go up above what we have calculated, or maybe it will go down. So what we will do on Monday, Wednesday, inshallah, is that we are gonna have a better weight estimate. We will get a better estimate of the weight and a better performance analysis. We will check all the requirements again. Did we satisfy them or not? If yes, let's finalize the design by putting maybe fairings and final touches and optimization. That means improving performance. If not, I have to change something. Maybe I can make the wing a little bit bigger. Maybe I can add winglets. Maybe I can make this landing gear bigger and so on. And this cycle would go on until everything is satisfied and we move on. The one thing that we will not do is that we are not gonna go and do it again this semester. In 4 to 7 we do it twice, but in here we do it in a single row. So we will check the performance on Monday and we will see if it satisfies or not, make adjustments, and that will be the end of the project. Any questions, Ishmi?